Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Requirements to EMC Components in Automotive. Our speaker is Loran Völkel. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find a chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve the event. And you will also receive the link to the presentation in the next few days, and the recording will be available at our website shortly. But now I will hand over to our speaker, Laurent, and I wish you an exciting presentation.
Thank you, Marie. Now I will start to share my screen. I hope it will work. Can you confirm everybody can see it?
Yes, perfect.
Okay, thank you. So hello everybody, my name is Laurent Völkel. I'm field application engineer at Würth Elektronik, and I will present today some requirements for the passive components in automotive products. I think you saw me now, and I will close my webcam because it's need maybe too much bandwidth. So you will ask why automotive parts? Why you cannot take just the simple standard products? Well, finally, they are very similar to each other. The only one thing is the automotive products, it have been much more often tested, and they are passing all these requirements like a PPAP. We have an IMDS entry. They are produced in a plant where ITF 6949 qualified is, and finally they are qualified according to Aecq 200. What means all these different short numbers and abbreviation like WEASP? EASP, like I wrote on my slide, is also calling Automotive Standard Products. So at Würth Elektronik, we did define components which are standard from stock, and you can get them from stock, which are produced according to this TS 6949, which was until 2017 valid. Now the most manufacturers are qualified already to the International Task Force 6949, which are something similar like the ISO 9001. If you are industrial customer, you need actually this ISO 9001 qualification. Yeah, it's a totally quality management. The IMDS, this is the International Material Data System, which was quite in the early stage. If I'm not remember wrong, it was 2005 when we start to be listed in IMDS, because it was starting for this lead-free components, starting from Japanese manufacturer, and later more like 35 OEMs are already in this system, and over 120,000 supplier. So actually this is nothing else, just a database. Then we have this Aecq 200, which is the Automotive Electronic Council. The 200 is referring to the passive components, the 100 to the active components. And PPAP is nothing else, just a documentation, actually a production part approval process. This is kind of paperwork specific where you can additional make the test and you can supply all the results. So when we are supplying a PPAP level, there are more like there are 5-level nodes, but we are delivering 2 different levels according to this Aecq council. Actually, the level 1 and level 3. What is the big difference? By level 1, you get this part submission warrant, you get the data sheet, and you get the rows and reach documentation. By delivering components in level 3, which is the most of the component, I would say 99%, you just get a little bit more I would say documentation like FMEA, you have a control plan, flow chart, the test results, and of course also this sampling process and yeah, much more information, much more details like in the level 1. This product part submission warrant actually is nothing else, just kind of contract between the manufacturer and the customer. It's very important when you get this documentation that our is always signed, but you have to sign this documentation, send it back. If you don't do this, it's not a valid documentation. Many customers forget that, and that's is a part which is very important for the PPAP documentation. By the PPAP level 3, you don't get only just one datasheet with one single part number. When we make a documentation in PPAP level 3, you will get the whole product family. What means that? If you use, like example, a 10 microhenry inductor, and in the future you will need 4.7 or maybe 100, you don't need again to request again the whole documentation and everything, because in this size, in this product family, you get with one PPAP level 3 documentation the whole range what we are producing. This is another example of this Aecq overview for testing. You can see here the different sizes, the different numbers which have been tested, mostly military standard, some other one is a JEDEC standard, and you can see also they are always passing, like solderability, board flexing, mechanical shock, also ESD, which make no big sense to our components because it's not sensitive. But anyhow, we make all the possible tests which is described in this Aecq 200 testing method. For the IMDS, this entrance of this database, if you open the platform and you look for a part number like here, oh, I just realized this in German. Please forgive me that is listed in German, but you can put in English language as well. If you list, like for example here, the PDA inductor, and you choose one of these components, you will see almost on the atomic level what contain this component. Like the wire copper, which is 100% wire copper, it's contain also 0.35% phosphor. That's the copper. It's not pure copper. Somebody tell me this is not existing, just a pure copper wire. And you have also some tin and also the ferrite and the plastic base. And for each you have every entrance here, you just have to check the component and then to accept it, and that's it. The IATF 6949, this is the following from the TS 6949. This is suitable for the whole supply chain because the parts are manufactured in this IATF 6949 facility. The Aecq 200, they are having some sub criteria, like for fuses is something like 006, for some uh, polymeric resettable fuses is 004. So when you get the Aecq documentation, you get everything what is possible to be tested for this component what we are producing, and this is really related to this component. You will see that in the documentation. There are some different temperature grades. We deliver 4 different temperature grades. Grade 0 is operating temperature 150, and grade 3, which is only 85. And we have something like grade 2, which is 105, a little bit unusual, but this is a need for some plastic enclosure, like the snap ferrites cannot withstand 125, and then we have 105 degrees Celsius. When we talk about temperature degree, it's also important that you read the data sheet and you understand the meaning why when we say a rated current and operating temperature and storage temperature can be high differential between each other, because when we say a maximum operating temperature 150 degree, which is grade 0, it means when we apply to these components 22.5 amp, the component will produce himself 50 degrees self-heating. So if you have 150-degree ambient temperature, you cannot apply any current to this component because this component will overheat and will be running out of its specification or even damage it. It means if you want to apply the maximum current, you can have a maximum ambient temperature of 100 degree, because 100 degree ambient temperature plus on top the self-heating of the component, it will reach the 150 degrees Celsius. The storage temperature, it's very opposite, minus 20 degrees Celsius plus 40 degrees Celsius storage. And you will wonder, oh my God, how is possible that we can store only we can operate 150 but store only 40 degree? Yeah, because it's on original packaging. We deliver this component in tape and reel, and if you want to be able to solder this component on PCB, you need to take care that this plastic, this tape, is not so good if you put to minus 40 degree, because it can break. And if you put more like 40 degree, it maybe could damage the glue on the tape, or it could damage something on the on the reel. So that's the reason why we deliver tape and reel. As soon you solder this component to the PCB, it's starting the operating temperature. You can store it even if you have a storage in Sahara somewhere by 80 to 100 degrees Celsius. I think it's not possible to have a warehouse with 150 degrees Celsius. But in Siberia, I can imagine you can have a warehouse without heating by minus 55 degree. But this is also very obviously so you will not have. So take care about this maximum ambient temperature, because if you have an ambient temperature like 125 degree, you cannot apply anymore the maximum rated current. You must use a derating. So you can derate the current, and if you take care about derating the current, you will be able to reach the 150 degrees Celsius, and then it's no problem to use this component. There are some different components in EMC and also for assembly, which are standard automotive products. There are different power magnetics for storage or for filtering in form from inductor, and also from RF components, which are multi-layer ceramic inductor for automotive application. You may ask why we use so different materials for our ferrites. Why we don't use only nickel zinc? Well, nickel zinc is quite very useful, but we found out that in a lower frequency between 1 to 10 megahertz are existing different materials like magnesium zinc. And magnesium zinc until 10 megahertz have a much better performance like nickel zinc. Above 10, 20 megahertz, you cannot distinguish anymore. But for lower frequency, magnesium zinc is much more effective. If you are filtering something less than 1 megahertz, then is the manganese zinc the right solution. And if you want to filter something in deep kilohertz and you want to have a very large bandwidth, then you can combine manganese with magnesium, or manganese with nickel zinc, 2 ferrites, or you can take only just one ferrite core made from nanocrystalline. Nanocrystalline have the highest permeability and the most bandwidth to cover a lot of frequencies. There are different manufacturing processes, like nickel zinc ferrites are a sintered ferrite. You take the different oxide, press together, put in the oven, bake them in the baking on 16 to 19 hours, and you have a very good reliable ferrite up to 150 degrees Celsius, non-conductive surface. You don't need to coat them. Exceptional for EMI for several hundred of megahertz. You can use that for EMI problem. If you still have some problem in less than 10 megahertz and you want to avoid to put too many turns on the nickel zinc ferrite, you can ask our colleague in sales department for the magnesium zinc, because magnesium zinc in this frequency you can see both are measured with the same fixture, with the same setup, the same size, and you can see the magnesium has much better performance in the lower frequency from 1 megahertz up to 10-20 megahertz. Above 10-20 megahertz, they are very similar. And the maximum temperature is not 150, just 140, some disadvantage. If you need to filter something below 10 megahertz and in lower kilohertz, even less than 1 megahertz, then you will need manganesic zinc. Manganesic zinc ferrite is also sintered ferrite, but he is conductive. That's the reason you will get them always coated. This coating is necessary because the surface is high conductive, and if you make turns to not making some short circuits on the surface or to have some damage on the wire, and you can use that with a coating, and then it's no problem. The coating is also made in the oven, so it's baked to the ferrite up to 150-degree operating temperature, no problem. Now, if you have even less than 1 megahertz and lower kilohertz frequency or some problem, or you still use a manganesic zinc with maybe 5 to 10 turns, and this is not so possible in the mass production when you have wiring wires for the cars, or this is sometimes not so optimal to use that in the mass production. You can ask for the nanocrystalline core. The nanocrystalline core have a permeability up to 100,000. In comparison with a manganese zinc, which is 6,500, and nickel zinc, which is maximum 1,500, you can see this nanocrystalline core have extremely high permeability. Because of that, to reach the same inductance value, you don't need to put 10 turns like nickel zinc or 5 turns by manganesic zinc. Maybe it's enough to put one single turn and sometimes maximum 2 turns, and you have an extremely high AL value, and you have an extremely high nice inductance. Because you don't put so many turns, you don't produce winding capacity, and you have a best bandwidth possible reachable. But nanocrystalline core are not sintered material. It's a special manufacturing, and that's a reason why it's just pure metal alloy in fluid form, cooled down in shock, and then make this crystallization. And it's high conductive. That's the reason we don't coat them even, because they are also pressure sensitive. We put them into the plastic enclosure. It's a plastic housing, completely plastic, which is keep this force for winding strength away, and also keep the component very safe for short circuit or for moisture that doesn't have rust or something. Because of the plastic, only 125 degrees Celsius operating temperature, but because of not sintered, they have no drifting like the sintered materials in a temperature from minus 40 to plus 85 degrees. What's happened in these ferrites, actually, we have this energy conservation law. This EMI is also a force, is also energy. So we take this energy and transform these two vectors, which is a magnetic field and another vector is electric field. We transform them into the heat. So actually the ferrite transform this energy into heat. But believe me, honestly, you will never be able to make such measurement by a thermal camera using to see if your EMI is have been transformed to the heat. By automotive, you can overheat the ferrite only by the um, testing when you make immunity test. When you make 400 volts per meter immunity test and you apply this ferrite like a filter to the cable, it could happen during the immunity test that you can warm up the ferrite. If the ferrite running hot, you make something wrong, it should be never running hot, but only at immunity test. By radiation should be stay cold. Please don't produce devices which making the ferrite running hot. This is not EMI problem, this is also a safety problem. To solve the problem on the PCB level, it's much more better if you can solve that on the PCB level. And on the PCB level, the cheapest component is called also chip bit ferrite, not cheap, is chip. They are the ferrite bits, and you can apply these ferrite bits up to 8 amp in different sizes. Okay, 0402 is not the best to solder by hand, but Würth Elektronik produce also up to 1812 sizes, so we are not stopping at the 08 or 05 size like many other competitor. You will get them also in the bigger sizes, no problem, with excellent filtering efficiency and low cost on the PCB. If you know exactly where the noise is produced, this is the easiest way to uh, absorb them. How a ferrite looks inside, this is a small computer tomography, this time not on my bones. On the chip bit ferrite, this is a 0603 size, and you can see the internal layers. They are pure silver layers, and you have the two electrodes left and right where are contacted. That's how chip bit ferrites are made, the standard ones. Then we have some very special one. This is multi-layer power suppressor um, ferrite beads, which are also pulse tested. If you go to our web site and you open the Red Expert section, you will see that on also the data sheet is described. These ferrite beads we give information about how high can be this inrush current for a short time. So we give amps and time graphs where you can know that this ferrite withstand this load dump test or withstand this inrush current when you start your computer or your electrical motor, and you have a nominal current like 10 amp and up to 20 times higher you can apply the inrush current. And if you see in the graph this is more like 100,000 times, then you can sleep over the night safety and good because it will not be damaged. By the standard chip bit ferrites, maybe you will find out that sometimes they are um, overheating by the inrush because you overload them by the current. And if you apply pulse on that, maybe it will be damaged by the MPSA. There are pulse specific manufacturers that are not destroying each other. The dinosaur of the automotive components was this rod core through-hole technology. You will find them very often in many different applications. I count last time in an electronic seat 62 pieces of those and one seat. It was crazy to see that every each motor, DC motor, have two pieces of them, and lot of components of them are mounted because they are very low cost and very effective if you place them exactly where you need. But this through hole is not so easy to handle. Mostly you will need hand soldering or wave soldering is working also when you have a PCB. But if you have a PCB, I would recommend use the surface mount version. We have them with a small plateau, and that can be pick and place automatic in tape and reel and much more easy to handle them. A nice example from a customer who did not pass the conductor emission with a motor, electrical motor, and he using that kind of rod core inductance. We changed them from rod core inductance to the shielded version, and then he passed the EMC test, and you can see the bottom line is the noise floor of his receiver. So he was coming from this noise to that noise, which is a big step sometimes. The difference between this shielded and unshielded version, it is just because we have this shielding ring additional. And this shielding ring make that the magnetic field, it's getting back into the core very fast. And this is an example measured here in Waldenburg in our own EMC lab. You see here a DC-DC converter using a storage inductor, the unshielded version. And if you solder the same value but shielded version, the conductor emission is dropped to 90 dBm down, so it's better in conductor emission. In the anechoic chamber, in radiated emission, you can see by the picture, I think it's speak by himself. Left, not shielded, right, shielded with radiated emission measurement. The PDA, this is the one of the inductor which is the most best shielded inductor and very reliable, made from nickel zinc, goes up to 1 millihenry. And another version is the PD only without the A. The big difference between PD and PDA is not the core. Core is absolutely same. The wire is almost same. The difference is the base. The PDA has a plastic base and the PD have a metal base. And because using two different base, by the plastic base, we are welding the cable, the wire from the inductor to the um, base, this electrode, so are welded, not soldered. And when we use a metal base, we are soldering them. Using soldering, we can use multi-wire, bifilar wire or trifilar wire. By welding, we can use only one single wire. Because of this, we can go up by the PD up to 2.2 millihenry, by the PDA only up to 1 millihenry. It fits to the same footprint, and this is absolutely same effectivity in core losses, and the DC resistance because of the wire sometimes will differ. The unshielded version is the PD2A, which is just a drum core with wire and no plastic or metal base. Is directly vulcanized or actually metallized uh, electrode here with the wire, with the tin. And this is very simple. If you use the size 7850 on your PCB and you find out, oh my God, I used the cheap version without shielding just to saving few cents per pieces, you may have the luck that we have the 7550 with the same pet size and it fits the same design with the shielding ring. Only this size, I'm very sorry, we have tooling only just for this size, and you can have them also with the shielding. And if your inductor was the EMI root cause of the EMC measurement, you can have them also with a shielding ring, but only this 7550 series. The best shielded inductor in terms of no air gap on top or bottom like the PD has is the Maya. Maya is not a ferrite sintered material. This is a metal alloy, which when we produce them a little bit different the standard inductors. You can have even some of those in high temperature, 150 degrees Celsius. And when during the manufacturing, we make first this air coil. This is a wire-made air coil. Then we put this air coil in the tooling with the powder together, and we press them together, and that's it. We are not sintered material. The air gap is a distributed air gap inside this metal alloy. Have an excellent saturation. In fact, on the smallest volume, the best inductor which can be reached. CHSA are actually a rod core inductor which you cannot see it, but it's a shielded rod core inductor. It's using a flat wire, you can see here inside, we're using flat copper wire with a plastic base, and we put this shielding around him, and you have a small gap here and small gap here, which is make the saturation point. And this is good for EMI because it has no magnetic field which can break out. Just a little bit opening here on the plastic base, which is considering almost nothing because you have always a PCB anyhow, which make problem. And this is the best shielded inductor for rod core and service mount possibility. The HCFA, this is the biggest inductor which can go up to 81 amp. We have some inductor in this area which will go up to 150 or up to 150 amp. The next bigger sizes will be available soon as well, and they are excellent in saturation point. It has 3 points to solder. Two of them have to be connected because inductor input output, and the third one is just for mechanical fixing. You don't need to put that special to ground or somewhere. This is just to be soldered for mechanical fixing, that this heavy inductor will not fly away from your PCB board. The HCIT are again such rod core inductor with a shielding, but through hole technology, not so exceptional big values, mostly for very specific application. If you do anything by RF high frequency, you will need some multi-layer ceramic inductor, and we have even the polarity marking. It means beginning of the winding, because if you work in gigahertz area, this parasitic, which is given from the internal layer to the ground coupling, make a parasitic capacity, and maybe you have to consider that. So we have the marking of beginning of the winding, and 180 degree of the other side. It's of course of the other side because this is the beginning of the winding if you take from this direction. Some other component which is actually not a real passive component, that's the reason why we cannot supply PPAP level 3, only just PPAP level 1, are this mechanical assembly component, which is again a spacer, which are possible to be soldered, tape and reel. So it's SMD placer, which you can solder, and you have a different length. And if you want to use that also for with a screw, a thread, you will have that also in the M3 size with different lengths, and you can ask for a few examples. The next component which you can use, it is this finger contact fingers, or copper beryllium with a nice gold plating to have a very low DC resistance. In some application where are multiple PCBs stacked to each other, so one application where the customer used some connectors, and the problem was that during the vibration test that the connector was making not a good contact. We changed that to this contact finger on the PCB on the top. Just put some gold plating on the contact surface, and much lower cost and much reliable and very easy to assemble, pick and place from tape and reel, and very low DC resistance. Some automotive kits, design kits are on request from the salespeople available. Just ask please for these design kits. And if you want to have a nice place where to uh, keep them on the same place, and not just throw from one side to the other side on your desk, you can ask also for this uh, racks. You can put that very nice to the wall, and you can individual ask for different sample box. And if you have an EMC lab or you make a development, this is a nice place. More information you can get from this trilogy of magnetics or LD Spice book and some different application books. And if you want to have any other questions, or you want to be in touch with me, I have also a Twitter account, a LinkedIn account. If you go to our YouTube website, you will see some nice videos where I'm explaining some saturation points of inductor, how it's measured, or what is the nominal current, and so on. I think that was in a very fast version my presentation. Now, if you have any question, I will open now the chat function and see if there are any question. Let me see.
Yes, thanks a lot, Laurent, for your interesting presentation. As you already mentioned, we would like now to turn our attention to your questions. So feel free to enter your questions in the chat function. Laurent is here for you to answer them. Okay, Laurent, let's start with the first one. Are all
Yes.
components with AEC Q200 tested allowed to be used for automotive applications?
Well, if a component is AEC 200 tested, it's not automatically a product which is good for automotive. You will see in the future many our products will be AEC 200 tested, but they are not part of the automotive standard products. To be used for automotive, it needs to be the whole process, the whole production chain must be according to this IATF 6949. And because of that, AEC 200 is just a minimum request to the component to be tested. We test several years already our components more like AEC 200 are requesting. One of the requests what we are testing is like we test 5-time reflow process to be able 5 times to the reflow, and AEC doesn't request that. So not AEC 200 automatic is our automotive component. So don't use this like that.
Okay, thanks. And another question, why need some cores this coating?
Okay, coating, it's a need because when you put wires on the core and the core surface is conductive, it could happen that you are scratching the lack of this winding, or the isolation will be damaged. And because the core is conductive, you make a short circuit of your winding. If the core is not nickel zinc or magnesium zinc, which is not conductive, it's like a ceramic core, or if you use a wood, whatever you want to use wood for an inductor, you don't need to be coated. You don't need to coat the wood. But if you use iron powder cores or If you use manganesic zinc cores or any other core which is conductive, you need to be coated. You need the isolation. The nanocrystalline, they are packaged in a plastic enclosure because only just the coating is not enough. They are sensitive to pressure and they can break easy. That's the reason we need a stable mechanical plastic enclosure. But all conductive surfaces need to be isolated, coated. In transformer, use a plastic bobbin and you put tape on the core to because the plastic the core of the transformer, mostly manganesic zinc, is also conductive. Just take your probes from your multimeter, put in mega ohm, and scratch on the surface of your transformer. If it's measuring kilo ohms or hundreds of ohm, is manganesic zinc. Is not, is nickel zinc.
Okay, cool. So, Laurent, I think your presentation was clear enough as there are no questions left. And I would say we are finished with this presentation now. And if there are any questions left, you can also send them to us via email for sure. And for now, I would say thank you very much for your attention, and we hope you enjoyed the presentation. The next presentation topic is our Q&A with Lucas Di Grassi and René Rast, the drivers from Formula E Audi Sport up Scheffler. So maybe see you there and enjoy our digital days. Goodbye.
Bye.